Hello everyone, welcome back to ECE350 lecture 12. Today we're going to talk about transformation between coordinate system like Cartesian coordinates, cylindrical coordinates and spherical coordinate system. How do you go back and forth between them? Gradient of a scalar vector, and in the part 2 of the video we're going to talk about divergence of a vector and curl of a vector. So XYZ is in your Cartesian coordinate system. From there, you can easily go into cylindrical coordinate system if you need to find the radius, right, r, and also angle phi. So cylindrical coordinate system is r phi z, right? So if you know r phi, you can easily go from Cartesian to cylindrical. And if you go from cylindrical to Cartesian, you just need the x and y. X is r cosine phi, and y is r sine phi, right? So over here, you will see that how r hat and phi hat, the unit vectors, could also be found. So r hat over here is basically between x hat and y hat. So x cosine phi and y sine phi. And your phi hat over here is also between negative x hat, right, and y hat. So this is the same, this angle and this angle is the same. So it will be negative x sine phi plus y hat cosine phi, right? So you can go back and forth. There's a table over here. So you can go from Cartesian to cylindrical over here, for example, and you can find r, z doesn't change, r phi, and all unit vectors here and vector components. So ar, a phi, az. So ar for cylindrical coordinate system, if you go to cylindrical coordinate system, this is r component, phi component, and z component. Z component is the same, so az equal to az, the same thing, but these are two different coming from your x, y, z. So ax over here, ay over here, x over here, ay here. So that's how you go back and forth. We're going to do an example to show you how it works. All right, so right here. So we have a point in Cartesian coordinate system and also have a vector in Cartesian coordinate system. How do you represent this point in the cylindrical coordinate system? Also, how do you represent this vector into the cylindrical coordinate system? So as you know that from this one, I have to find the r. So r is x squared plus y squared, and square root is 5. So 3, 4, give 5, right? I have to find the angle. Angle will give a negative 50 degree, right? 53 degree. So z is same. So you have r here, phi here, and z here, right? So that's your cylindrical coordinate system, r, phi, and z. Now for this vector here, this is your Cartesian coordinate systems, and in your cylindrical coordinate, this is the vector, right? R hat, ar, phi hat, a phi, z hat, az, and this z is the same thing. So az before, as you see here, az before, right? So how to find this ar and a phi? So if I go back here to the table, look at here, ar and a phi, right? Right here, right? So I'm going to use these two equations to find ar and a phi. So ar, have the equation here, and this ax coming from this x component here, who is 2, and ay coming from here, which is negative 3, right? So 2 cosine phi and negative 3 sine phi, and same with the a phi, right? So now to put it together, so you have r hat, then your a phi over here, so a over here, phi hat, and here's your a phi and z hat z. So if you know the angle, then you can put it all together here as your cylindrical coordinate. So this is in the cylindrical coordinate system. So you can use the previous table to go from one coordinate system to another coordinate system. And I'll ask you to do this. This is going from your cylindrical from here to your spherical coordinate system. So that's what you're using. All the equation you can find it from the previous table. And also distance between 2 points in Cartesian, in cylindrical, and in spherical. So now we're going to get to the gradient. What is the gradient? Gradient is basically you apply the gradient over a scalar function, something happens. So it provides, a gradient provides direction to a scalar function first. So gradient provides direction to a scalar function. First thing. Second thing, direction, the gradient direction is the greatest change of the function. So this is the greatest change. So let's me put it this way. Direction of the greatest change of the function also provides that that direction is direction of the greatest change of the function, of the scalar function. So in Cartesian coordinate system, this is the gradient of t. T is a scalar function. T is a scalar function here, and the del factor here is the gradient of. This is the del factor. When I apply the del factor on the scalar function t, it becomes the gradient of t, or grade t or gradient of t. So del function is this one over here. This is in the Cartesian coordinate system, and cylindrical coordinate system, spherical coordinate system, they have their own del function. So that is what is your gradient, right? So now you can find this is the greatest change. This is the greatest change. This is the greatest change of the t function. T scalar function will change the highest value in this direction right here. Okay, but if you want to find the direction change in the particular direction, if you know that direction, like say dl over here, if you know that particular direction, right, dl, then you can find the change of the function t in that direction by basically taking the dot product between gradient t dot a particular direction. Okay, so as I was saying, if you try to find a change of a function in the particular direction, you can find it by taking the gradient of t and unit vector in that direction. You can multiply them, you get to find the change of that function in that particular direction. So here, this is the function of the temperature over here. All right, then I will try to find a change in this direction over here, and evaluate them at this point, right? So first I have to find the gradient of the temperature function, which is right here, right? Then I need to find the unit vector in this direction here. So I have a vector. If I multiply that vector with its magnitude, I get the unit vector right here. This is the unit vector in direction. So now if I take a dot product between this one and this one, right, I'll get the change of the function t in this particular direction. So I'm taking dot product here. If I take dot product, this is the change of that function in that direction. Okay, so now if I evaluate that at this point over here, put the point back, this is the change of the function t in the direction of right here, and at that point. That's how you find a change in direction in particular, change of a function in the particular direction. You can evaluate them at any point in that direction. That's all for the this part. I'm going to get to divergence and the curl in the next video.